Now we can start working on the way the smoke looks by changing the particles into sprites. Here's where we start applying more of the topics discussed at the beginning of Chapter 2, such as what happens to the particle's density and size as it gets older. Before I go any further, I want to turn on depth sort in the particle's attribute editor. This tells Maya to render the sprites from farthest to closest, which eliminates unpredictable transparency layering during hardware rendering, which we'll cover in Chapter 5. I first need to create a number of per particle attributes which deal with the sprite's characteristics. These first four attributes I can create using the built-in particle attributes. Sprite num pp, so we can use different images on different particles. Sprite twist pp, so we can spin the particles. Sprite scale x pp and sprite scale y pp to control the scale. Opacity pp to control the opacity. Now I need to create some custom attributes. Twist mult pp, which will give us a variation in each particle's rotation. Init scale pp, which will help the simulation remember each particle's target scale. And init opacity pp, which will help the simulation remember each particle's target opacity. In the smoke's creation expression, I want to declare values for these attributes. I initialize each sprite's rotation with a random value between 0 and 360, then I declare a multiplier to use in the runtime expression called twistMultPP, which won't take effect until I utilize that attribute in the runtime expression. The SpriteNumPP attributes gets a random number between 1 and 5. Remember, the rand function will return a number greater than the first argument and less than the second argument. If I had set my rand function to be between 1 and 5, the function would never return exactly 5. I'm also using the trunc or truncate command to strip away anything after the decimal place. The opacity of each sprite will fade as it gets older, but I want to define an initial target value for each particle's opacity pp attribute. Over time, I'm going to modify opacity pp, so I'm declaring init opacity pp to remember its initial state, no matter how opacity changes. I can view these values if I set my particle type to numeric, then enter the attribute I want to view. If I view SpriteNumPP, for example, I should see a nice distribution between 1 and 5. When I change the display type to numeric and add attributes for that particular display type, the attribute defaults to particle ID. In this mode, you can view each particle's unique ID. Remember, that particle ID attribute is zero-based, meaning that it's a list that starts at 0. Also, each particle has an ID that is unique. Once a particle dies off, its ID is never used again by a new particle. Before I go any further, I need to apply a cloud texture to my sprites. I've created 5 slightly different square cloud textures, each of which has an alpha channel that fades off to black on all 4 sides of the image. I'm going to create a simple Lambert shader, as well as a file texture node which plugs into its color channel. The only attribute I want to change on the Lambert is its diffuse value, which I'll set to 2. Cranking up the Lambert's diffuse attribute to a number greater than 1 dramatically increases the particle's brightness in the hardware renderer. I've assigned each particle's SpriteNumPP attribute to a random value between 1 and 5. I can now use that value to determine which image gets mapped onto which sprite. In the File Textures attribute editor, I'll browse for an image in my textures directory called SmokeSprite1. This image was created with a simple 2D paint package with a soft-edged airbrush. The image's alpha is identical to the RGB channels. Note that there were 4 other cloud textures in the same directory. I have to turn on Use Frame extension and set the Use Hardware Texture Cycling values to start at frame 1 and end at frame 5. I have to remove the trailing frame number from the file name, as Use Frame extension adds the required frame number to the file name for me. This setup doesn't necessarily tell Maya to cycle through all the images, it simply makes all 5 frames available to the shader. Finally, I have to keyframe the frame extension attribute, which in turn sets up the file texture to allow the particle object's SpriteNumPP to call whichever texture is being assigned. I key the attribute at a value of 1 at frame 1 and a value of 5 at frame 5. I'll assign this shader to my sprites. Now, I want to add scale control to my sprites in the creation expression. Because the particles will originate underneath the tires, I'm going to scale the sprites from 0 as soon as they're born. By the time the particles are a few frames old, they'll be out from underneath the tires, so they should be scaled up by then. I define the sprite's destination scale value with init scale pp, then set their x and y scale to 0. If I play back now, I won't see anything as the sprites are scaled to 0. Now, I want to add the smoke's runtime expression. First off, I want to scale up the particles as soon as they're born to their init scale value, then scale them up even more, but slower. I'm using a simple conditional statement to grow the particle to its target scale, which we defined as init scale pp in the creation expression. In the first line, I'm saying, if the particle is less than 7% of its lifespan, execute the next line. To scale it up, I'm using a smooth step function, which simply returns a value between 0 and 1. It takes in 3 arguments, a min, a max, and a multiplier, which is the number you want to evaluate. This line says, when the particle is born, return 0. When it's 7% of its lifespan, return 1. I take that smooth step function and multiply it by init scale pp so that by the time the particle is 7% of its lifespan, the particle is fully grown. It's called smooth step because the resulting value is nicely distributed in a spline-like curve. You can learn more about smooth step as well as other mathematical functions in Chapter 10, as well as the Maya dynamics documentation. When the particle is older than 7% of its lifespan, the else statement takes over. This line is similar to the second line, however the minimum value for the smooth step is not 0, but 7% of the particle's lifespan, and its maximum value is its lifespan. Instead of multiplying this by its target scale, I'm multiplying it by only half of its target, then adding that value back onto its target scale. This gives me a slow scaling of each particle as it grows older. The final line tells the particle's height to always match the particle's width. Now, let's add a twisting effect to the smoke. I'm using another smooth step function here. This time, I'm taking the value I defined as twistmult.pp in the creation expression and adding a value to it for a bit of acceleration. However, that value is being increased over time, so we see a slight increase in the particle's spin as they get older. Now, I need to fade out the particles as they get older. It's imperative the particle's opacity is 0 before they die, otherwise you'll see particles popping away as they disappear. Again, a simple smooth step, but this time, instead of going from 0 to the target opacity, I'm going from the target opacity to 0. I do this exactly the same way as the scale, except I take the smooth step's result away from the particle's init opacity pp. Finally, I want to control each particle's size depending on its proximity to the ground. The closer to the ground plane the particle is, the smaller it should be. I have to query the particle's position. Here, we want to address each particle's position in y, so we have to extract that value from its built-in position attribute, which is a vector. In the second line, we're using linstep, which is similar to smooth step, except it returns a linear distribution between the min and max values. This linstep uses the particle's y position as its third argument. So, in natural language, this line reads, if the particle's y translation is less than or equal to -4, return 0. If it's greater than or equal to 5, return 1. Otherwise, return values in between. This in turn is multiplied by the target scale for the particle. If the particle's really low, it's scaled to 0. If it's sufficiently high enough in the air, it gets its full target scale.